This video will show how to calculate the pH of a weak acid, a weak base, and a salt. First, we will calculate the pH of 1.02 molar formic acid. Formic acid is a weak acid. The first step in solving the pH of a weak acid is to write the chemical equilibrium. The chemical equilibrium includes the dissociation of the weak acid into H+ and its conjugate base, formate. The next step is to set up the ice chart. I stands for initial. The initial concentration of formic acid is 1.02 molar. The initial concentration before dissociation of H+ is approximately 0, and the concentration of formate is 0. The change as formic acid dissociates is denoted as -x, +x, and +x. The -x is because the formic acid concentration will decrease. The +x indicates that the H+ and the formate concentrations will increase. Then at equilibrium, the formic acid concentration will be 1.02 minus x, the H+ concentration will be x, and the formate concentration will also be x due to the 1-to-1 stoichiometric ratios. The third step is then to determine whether to use the quadratic equation in solving the pH. In order to determine this, we divide Ka, the equilibrium value for formic acid, which is 1.8 times 10 to the minus 4, by the formal concentration of formic acid, which is 1.02. When we divide those, the quotient is greater than 10 to the negative 4, which means we must use the quadratic formula to solve. The fourth step is to write the equilibrium expression. Ka is equal to the products divided by the reactants. In our chemical equilibrium, the products were H+ and formate, and the reactant was formic acid. We then substitute the values that we found in our ice chart at equilibrium. For H+, the value is x, and for formate, the value is x. So the numerator is now x squared. In the denominator, we have 1.02 minus x, which is the equilibrium concentration of undissociated formic acid. This ratio is equal to 1.80 times 10 to the minus 4, which is Ka for formic acid. Our fifth step is then to solve for x, which is H+ concentration. We cross-multiply our equilibrium expression, and we find that x squared is equal to 1.836 times 10 to the negative 4 minus 1.80 times 10 to the negative 4 times x. When we solve this for x, we find that x is equal to 0.01346, which is the concentration of H+ in moles per liter. The sixth and final step is to then solve for pH, where pH is equal to the negative log of the H+ concentration, which in this case is 1.871. The next problem is to calculate the pH of a weak base. Specifically, calculate the pH of 0.419 molar ammonia. Our first step, again, is to write the chemical equilibrium. Here, NH3, when it comes into contact with water, dissociates into NH4+ and OH-. The OH- indicates that this is a weak base. The second step is then to set up the ice chart. Initially, we have 0.419 molar ammonia. We ignore water because it's a pure liquid, so its concentration will not change. The initial NH4+ concentration is 0, and the initial OH- concentration is approximately 0. On the change line in our ice chart, we have -x for ammonia, plus X for NH4 plus, and plus X for OH minus. All of the NH3 that dissociates becomes NH4 plus and OH minus at 1-to-1 stoichiometric ratios. Then at equilibrium, we have 0.419 minus X NH3, we have X NH4 plus, and we also have X OH minus. Our third step is to then convert the Ka to Kb to determine whether to use the quadratic. Acid dissociation charts list the Kas rather than Kbs, but the conversion is simple. To determine Kb, we divide Kw by Ka, so 10 to the negative 14 divided by 5.69 times 10 to the negative 10 is equal to 1.76 times 10 to the minus 5, which is the Kb for NH3. Since Kb, 1.76 times 10 to the negative 5, divided by F, the formal concentration of NH3, 0.419, is less than 10 to the negative 4, we do not need the quadratic to solve this equation. Our fourth step is then to write the equilibrium expression. Kb is equal to NH4 plus concentration times OH minus concentration divided by NH3 concentration. Notice that for a Kb expression, OH minus should always be in the numerator. For a Ka expression, H plus should always be in the numerator. Again, we substitute the values from the equilibrium line in the ice chart. For NH4 plus and OH minus, the value is X, so the numerator is X squared. In the denominator, because we are not using the quadratic, we make the assumption that 0.419 minus X is approximately equal to 0.419 because X is sufficiently small. That makes our calculation easier. So X squared divided by 0.419 is equal to Kb 1.76 times 10 to the negative 5. Our fifth step is to use that equilibrium expression to solve for X, where X is equal to the OH minus concentration. In this problem, X is equal to 0.002716 molar, which is the concentration of hydroxide ion. Our sixth step comes in two parts. In the first part, we solve for POH. POH is the negative log of the OH minus concentration, which here then is 2.566. We then convert the POH to pH using the relationship that the pH will always be equal to 14 minus the POH. In this case, 11.434. We will now calculate the pH of a salt. Specifically, we will calculate the pH of 0.269 molar sodium formate. Our first step, as always, is to write the chemical equilibrium. This is a bit more difficult than it is for a weak acid or weak base, because we have a salt, which is a combination of an acid and a base. For example, when hydrochloric acid is mixed with sodium hydroxide, the product is sodium chloride plus water, or a salt plus water. In this example, the chloride ion is the conjugate base of HCl, and the sodium ion is the conjugate acid of NaOH. These two form to make NaCl. If we mix a strong acid and a strong base in equal quantities, the salt will be neutral. As you know, sodium chloride salt is neutral with a pH of 7. However, if we mix a strong acid with a weak base, the salt will be acidic. The conjugate acid of the weak base is the weak acid. On the other hand, if we mix a weak acid with a strong base, the salt will be basic. The conjugate base of the weak acid is the weak base. In our problem, with sodium formate, we have mixed a strong base with a weak acid. Therefore, the conjugate base of the weak acid acts as the weak base. So formate, COOH-, behaves as a weak base when it reassociates to form formic acid and leaves behind OH- on the water. Therefore, when we mix the weak acid, formic acid, with the strong base, sodium hydroxide, to make the salt, sodium formate, the salt is expected to be basic. So the chemical equilibrium then is formate plus water reassociates to make formic acid plus OH-. Our second step, now that we've established the chemical equilibrium, is to set up an ice chart. On our initial line, we start with 0.269 molar formate. We ignore water because its concentration will not change. Our initial concentration of formic acid is 0, and our initial concentration of hydroxide is close to 0. On the change line, as usual, we place minus x on the left side and plus x on the right side for formic acid and hydroxide. In all of these examples of weak acids and bases, we have truly an equilibrium between the left side and the right side, but we are writing them with the arrow pointing to the right side to simplify the ice chart. Now on our equilibrium line, we have 0.269 minus x as our equilibrium concentration of formate, and x as our equilibrium concentration of formic acid, and x as our equilibrium concentration of hydroxide. Because we are solving for a weak base, we again must convert Ka to Kb to determine whether to use the quadratic. We divide Kw, 10 to the negative 14, by Ka for formic acid, which is 1.8 times 10 to the minus 4. The quotient Kw divided by Ka then gives us a Kb value for formate of 5.56 times 10 to the negative 11. Since Kb divided by F, the formal concentration of sodium formate, is less than 10 to the negative 4, we do not need the quadratic to solve because 0.269 minus x is approximately 0.269 since x will be sufficiently small. In our fourth step, we write the equilibrium expression. Kb is equal to the concentration of reassociated formic acid times the concentration of hydroxide divided by the concentration of formate. Again, because we have a Kb expression, we expect hydroxide to be in the numerator. We then plug in the values from the equilibrium line of our ice chart, where x is equal to the formic acid concentration and the hydroxide concentration, so x squared is in the numerator, and 0.269 is approximately equal to the formate concentration. We then set that ratio equal to Kb, which is 5.56 times 10 to the negative 11. Our fifth step is to then solve for x, where x is equal to the hydroxide concentration. Here, x is equal to 3.867 times 10 to the negative 6 molar. Since that value is our hydroxide ion concentration, we take the negative log of 3.867 times 10 to the negative 6, and we find that the pOH is equal to 5.413. We then convert the pOH to pH using the relationship that pH is equal to 14 minus pOH. Therefore, our pH is equal to 8.587.